All right. Okay. Well, hello, everybody. So very excited to be here. We're actually starting somewhat on time. So we're here today together with Sammy, who's right there in Zoom, going to talk about algorithmic fairness, talk about why it's hard, and talk about why it's interesting. I'm going to take off my mask. All right. So first of all, welcome. Thank you all for being here. Before we dive in, so happy Juneteenth. I know happy is kind of a complicated word to say about Juneteenth, but nevertheless, so just in case you don't know what Juneteenth is, just in case you're not from the US, so it's a holiday in the US commemorating emancipation of enslaved African American and Black Americans. And it originated in Texas on June 19th of 1865, so quite a long time from now, and it was only recognized as a US federal holiday on June 17th of 2021. So this is actually the second year that this is actually celebrated or acknowledged, I should say, as a US holiday. And so the reason why it originated in Texas, right, so this was the last proclamation that was signed abolishing slavery. It was in Texas. So we'll try our best not to run over time here, so you can join the festivities or the celebrations, the acknowledgements of this day. And also June 19th, Father's Day. So happy Father's Day to all of the fathers in the room, including Sammy on Zoom. So here's our plan today. So we're going to try to give you some insights into algorithmic fairness. We're going to try to find ways to connect some of your current work, so whatever you might be working on, to algorithmic fairness. We are deliberately going to try to be somewhat controversial, present potentially some devil's advocate arguments, and provide lots and lots of pointers through the literature if you're curious to learn more about any topics that we talk about. And of course, we'll share the slides afterwards through the website. What we will not do is even a remote attempt to do a complete overview of the area. So this is a subset of things that we sort of think are interesting or challenging to engage with, but of course, the literature is far, far broader than this. We're also not going to fully engage with the societal questions. So we're focusing specifically on algorithmic fairness, and there's lots and lots of work that actually sort of connects this more closely to social issues. So for example, this is my colleague at Princeton, Professor Ruha Benjamin's recent book called Race After Technology, which is a really awesome deep dive into some of the kind of root causes and then downstream impacts of bias in automatic decision making systems, so in AI systems. Also point out the FACT conference is the Fairness, Accountability, and Transparency conference is going on right now, so starting tomorrow actually in Korea, so at the same time as CVPR, so do check out some of those works for kind of a broader view of this space. We're also definitely not going to get everything right. So the conversations here are very complex and evolving. Also, some of the things that we say here may not age well, so just want to acknowledge that, and for the purposes of releasing slides, point me out. So this is June 2022, and if you're looking at these slides 2 months later, some of these things may already have changed. By way of just sort of brief introduction, just so you know who we are. So Sammy is on Zoom, so he's a researcher at Google right now, but he is actually faculty at Illinois, but about to become faculty at Stanford, so transitioning in fall of 2022. He's also the Black in AI president, and he focuses on developing the principles and practices of trustworthy ML, specifically ML applied to neuroscience and healthcare. And I am Olga Rosakovsky, so I'm an assistant professor at Princeton in computer science. I'm a co-founder of AI for All, which is a nonprofit to increase diversity and inclusion in AI. And I work on visual recognition, although I've done a lot of recent work on fairness and interpretability, and also have done a lot of work on data sets and vision and language, humans and AI, video understanding, and sort of other topics in computer vision. So the way we're going to structure the tutorial is around 7 common narratives. And again, these are not a complete set of narratives, but these are narratives that we sort of found interesting to discuss and engage with. So these are, 1, fairness issues only come up when working on people or people-related recognition problems. 2, once you define the metric, algorithmic fairness is straightforward. 3, bias in data sets is inevitable, need to learn to live with it. 4, problems with data set bias are getting better but worse. 5, the problem can be solved at the feature level. 6, fairness is a training data set problem. And 7, your favorite framework solves algorithmic fairness. we do not necessarily agree or disagree with these topics, and we'll give you sort of the pros and cons of all of this. So we spend a while thinking about what do we call these? Like, these are not really statements that we want to make. These are not really arguments that we want to uphold or take down. These are kind of narratives that are prevalent in the community in some way or other, and we are trying to engage with them and sort of give you some nuances about how to think about some of these narratives. So with that statement, I will sort of alternate talking about different ones. At some point, we'll take a 30-minute break, but let's just dive in and see how this goes. And we'll be pausing, of course, for questions, usually kind of at the end of every narrative. So I'm going to dive in with narrative number 1. So fairness issues only come up when working on people-related recognition. And this is a narrative that may be sort of particularly appealing if you kind of say, okay, I am just a researcher that's working on something completely different. Like, why should I care about fairness topics? I'm not working on people recognition, so it doesn't apply. And this makes sense in some way because fairness concerns, when we think about fairness concerns, right, a lot of them arise from situations when we are actually working on something related to recognizing people in photographs or something related to recognizing something about people. So this is, for example, a paper from ECCB of 2018, was one of the kind of earlier examples of algorithmic bias, where they're looking at photographs of people, and so the top row and the bottom row, the photographs look quite similar, except for perhaps the skin tone or race of the person top and the bottom image. And they're showing the predictions of a computer vision model for these people. And you might notice that the predictions are actually quite different. And in fact, at the top row, basically all of the predictions are basketball, even though for a lot of the images, there's actually not enough cues to predict basketball, but somehow the model is leveraging something that looks like it may be some kind of racial cues to make this prediction. And in the bottom, the predictions are sort of more diverse and more different, but again, appear to be correlated with perhaps with the race. So this is one of the kind of early examples of this, and there's also many others, right, of these kind of attempts to build computer vision systems to operate on photographs of people and the associated issues that come with it. So models that learn to quote unquote increase attractiveness by manipulating skin color. So this is a photo filter that you can apply to your photographs to make yourself more attractive, which is a whole other issue, is why somebody needed to build that. But given that it was built, the kind of really core issue was that what this filter was doing was manipulating skin color in trying to make the photo appear more attractive. Machines taught by photos learn a sexist view of women, so learned from a large data set and correlated the presence of people who appear to be female with certain activities. Facial recognition is accurate if you're a white guy. So this is seminal work by Joy Bellambini and Gebler that we'll keep coming back to, that sort of show the very large discrepancy in error rates of face recognition models on light skin, faces with lighter skin versus darker skin. And by large discrepancy, I mean the error rates were under 1% on faces with lighter skin and on the order of 13 or 14% on faces with darker skin. The recent controversy on Twitter around the cropping algorithm that learns to prefer lighter, slimmer, younger faces. There's also related concerns within image search results. And image search, even though this is not necessarily done using computer vision, but there is a lot of analysis, and we'll come back to talking about some of these papers about the sort of disparities in how search engines present people, again, from different demographic groups. And I'll highlight in particular a book called Algorithmic Oppression, How Search Engines Reinforce Racism. So this is a book by Sophia Noble from 2018 that again talk about how people, particularly, she talks about how Black girls are represented through search engines and how that sort of affects their lived experience. But there's other less salient concerns that are arguably also fairness concerns. This is not necessarily related to recognizing people or something about people, but for example, a few years ago, researchers started pointing out this lack of geographic diversity in computer vision data sets. So if you look at, we're sort of covering, let me actually remove PIN for a second here so that we can see more of There we go. So we can see more of this map. I'm going to move this out of the way. There we go. So this is a map of the world where darker regions correspond to countries that are more represented in computer vision data sets. So this is an ImageNet and Open Images, and lighter regions correspond to countries that are essentially unrepresented in these data sets. So for example, the entire continent of Africa is not represented. So what does this mean from a fairness perspective? So people have shown things like computer vision models are failing to recognize common household objects when those household objects come from different areas of the world. So for example, you build a computer vision system that you train on these standard data sets, and you claim that it's recognizing a common household object of soap. And then you show it a picture of bar soap, and it turns out that it actually fails completely. It has no idea what bar soap is because it's been trained on US brands of liquid soap, and that's what it's learned to recognize. And so this is an example where this is not necessarily related to trying to recognize something about people, but yet it has this, from your perspective, you're just working on object recognition, but actually it has this kind of problematic behavior that sort of not only is your system not working as well as you would like it, but it's not working in a way that kind of consistently disadvantages large populations in the world. And similarly, so in a recent paper, I'll also keep coming back to this because this is a paper out of my lab called Revise, which is a tool for measuring and mitigating bias in visual data sets. So we analyzed DDD 100K, which is a data set for autonomous driving. And we look at, so the graph here on the x-axis is the income decibel of zip code. So this is sort of across the region where these images were collected. We took the zip code, we mapped them to average income, we broke that up by decibels, and on the y-axis, we are looking at mean images per square mile for zip codes in this decile. And as you can see, right, it appears that most of the images come from the higher income deciles. So what does that mean? So it's not clear immediately, but this suggests that perhaps some of the models that we're going to be training on these data sets are going to be likely performing better in these higher income neighborhoods rather than the lower income. So how do you actually think about all of this in terms of like, how much of this, under what situations does something become a fairness concern? And how do we think about potentially sort of fairness related harms? So there's a great keynote by Kate Crawford in Europe's of 2017, and this is written up by Sarah Bird et al. In Microsoft Tech Report in 2020 called FairLearn. So this is a toolkit for assessing and improving fairness in AI. And they talk about fairness related harms, and in particular describe 5 of them. So one is that AI systems can unfairly allocate opportunities, resources, or information. So this is particularly relevant in a setting like giving out loans, for example. This is a common machine learning setting where this comes up, but arguably will become sort of more and more important in computer vision as well. 2, AI systems can fail to provide the same quality of service to some people as they do to others. And so perhaps the soap recognition example might fall under there. AI systems can reinforce existing social stereotypes. We'll come back over and over to this ideas we talk about sort of throughout the tutorial. 4 is AI systems can denigrate people by being actively derogatory or offensive. And 5, AI systems can over or underrepresent groups of people or treat them as if they don't exist. Okay, we'll be coming back over and over again to these kinds of frameworks. So the other issue I do want to mention related to fairness related harms is this questions about privacy and ethics in computer vision data sets. So we won't talk very much about it, but I do want to acknowledge this, for example, the work in WACV 2021 called Large Image Data Sets, a Pyrrhic Win for Computer Vision, where they talk about sort of some of the issues around the assumptions that went into the computer vision data set collection up until this point, and raised questions about consent and privacy and the ethics of sort of what guarantees do we make about kind of if somebody posts a photo of themselves online or a photo of their child online, does that mean that they've necessarily consented to that being included in computer vision data set and so on? And so consent and privacy are starting to become central in modern large-scale data collection. So this is, for example, there's a work passed by Yuki Asano and others published last year. So this is the data set meant to replace ImageNet for self-supervised pre-training. It's a data set that's collected without people, specifically to avoid these questions of privacy and consent. We did some work published at ICML this year, ImageNet Privacy Aware Face Blurring, where we took the ImageNet Challenge data set and blurred all of the faces of people in there, again, in an effort to protect their privacy and kind of show that this remains a very good benchmark, but now with these additional kind of loose privacy, not quite guarantees, but at least sort of attempts at privacy. The Ego4D video dataset that was released in February 2022, so they very much centered the idea of consent, and they collected consent from all of the participants, and it was sort of all structured specifically around making sure that this collection is done ethically. So this kind of brings me to the end of narrative one, right? So let's do like a quick discussion. So we've said fairness issues only come up when working on people-related recognition. So the pro kind of in favor of this statement is that there needs to be some kind of historical or social context for the issue to be fairness related, right? So it's often helpful to think about fairness from a harms perspective. There's a great book, Fairness and Machine Learning, Limitations and Opportunities. It's available online where you can sort of learn more about this. So I would argue that in order for something to be a fairness problem, right, there needs to be some kind of social or some kind of historical context around it. So if we're just working on, long tail distributions in object recognition, but without this connection to the world or to our society or our history, I would argue that that's not a fairness problem. So the con to this statement, right, is that fairness issues can be broader than one might think at first glance, right? So people related can be loosely defined. So this can be related to resource allocations, can be related to geography, underrepresentation. So this is not just about making predictions about photographs of faces, but it's much broader than that. And also I do want to say, so we can help address some of the fairness issues by working on tangentially related topics. So these are not necessarily fairness work, but it can help a lot in solving the fairness problem. So this is learning with long tail data, right? Learning with constraints, low shock learning, domain adaptation, improving the generalizability of models, interpretability. All of these topics can have a lot of impact and can do a lot of important work for the fairness space. So I'm happy to take questions on narrative one if anybody has any, and then I'll hand it over to Sammy for narrative two. Yep, go ahead.
Sorry for the question. The slides will be available?
Yeah, so we'll post the slides on. I mean, of course, we were editing the slides up until 3 minutes ago, so they're not posted. But yes, we'll post all the slides.
What's the working definition you're using for algorithmic fairness on these narratives?
So the question is, what's the working definition we're using for algorithmic fairness in all of these narratives? So that's a very good question, and I think that's going to change sort of throughout the tutorial, and we'll kind of move back and forth on that. And I think, in fact, the second narrative, so in the first one, I was sort of I was trying to engage with a very colloquial, sort of almost intuitive definition of this. It's an AI system that sort of did something that was in some ways harmful to somebody. In the second narrative, so Sam is actually going to dive much deeper into the actual metrics and sort of how do you define some of these metrics for algorithmic fairness. Yep. All right. Okay, so let's, yeah, any questions?
So I got that you covered the different threads within narrative one. I'm still a little unclear on what speaks for that narrative being true and what speaks for that narrative not necessarily being true. I wasn't able to get that from what you were.
Yeah, so the question is, so we covered a lot of the threads in narrative one and sort of what speaks for and what speaks against. So I think that is going to be consistent through the tutorial. I think that's part of the intention. There's no clear even for or against. It's sort of more about the nuances. So I would argue that what speaks for is that there needs to be some kind of historical context in order for this to be fairness issue. What speaks against is that it's broader than just working on face recognition or working on sort of any kind of recognition of people. You don't even need to have people in the photographs in order for there to be fairness issue potential. All right, so let me switch gears here. I want to switch to this camera.
Okay, we'll do some awkward transition to the next. Excellent.
I'm gonna have to stop sharing. Okay, maybe this is not the best idea with the camera, but I'm gonna do that. There we go. I'm gonna reshare screen.
Okay, do I get started?
I think so.
Excellent. So thanks, everyone. I'll continue the threads that Olga started. The main point of this second narrative, I think, is also very common. So it's the idea that the key question in addressing algorithmic fairness is a metric definition. And once you define that metric, the rest of the problem is solved. And similarly to the first, and like for all narratives, we're going to do a broad dive and attempt to show some nuance in the question. Before doing this, it's worth mentioning briefly that, one second, there we go. So as many of you know, there are lots of tools available for implementing fairness, given a framework and a metric, and I'll describe what I mean by framework in a few minutes. And so what's great about this is that if you're in a setting that has been addressed by existing work, there are simple tools you can just download and sort of get running within minutes in actually solving machine learning problems or other kinds of related algorithm problems with a fairness view within them. However, along similar lines, a lot of this work, the controls are a bit all over the place. We'll figure this out before the end of it. A lot of this work also allows you to think about the fairness question either pre-processing, so before actually training your machine learning models, so thinking about representation learning and things like that, as a way to, if you like, debias your data set. There's also work that implements machine learning at the same time as fairness mitigation. So these are typically called in-processing type methods. And then there are also what are known as post-processing methods, where you take a pre-trained model and then you try to change some of its characteristics in order to satisfy some notion of fairness that you're interested in. Now, maybe a broader view is that there are many steps when one is constructing a prediction algorithmic model. So in fact, one could imagine, or one could argue, that the issues or questions of fairness could show up anywhere in the machine learning or algorithm development pipeline. So this goes all the way from problem selection, and we'll dabble a little bit in this, but I think there's sometimes hard questions about which problems we should solve, and potentially settings where we should be thinking about whether a problem should be solved using other algorithmic techniques or not. There are interesting questions about data collection, which again, we'll spend a bit more time on, which center around the nature of the data and how this data could affect your predictions and how they can make fairness issues worse. The question is about outcome definition. In this paper, this is mostly thought of in terms of the goal of the, say, predictive model. I'm going to use it here to think about how you measure what your predictive or machine learning or algorithmic model is doing, and argue or discuss various ways of thinking about how to define good measures for when you're building your system, particularly with an eye towards fairness. The next and the step that's often discussed most often, particularly in conferences like this, are thinking about algorithm development. So here's the sort of meat of the problem where you're thinking about algorithmic tools you can deploy to address a certain definition or context. And then post-deployment considerations. So what do you do to make sure after you've deployed your model, things work reasonably? And I'm going to argue, I think, again, this might not be surprising to most of you here, that most of the work in algorithmic fairness is primarily thinking about the algorithm development piece. And so maybe partially to answer the previous question, think of algorithmic fairness as this algorithm development piece. I'll talk a little bit about how one can select better metrics and the effect this can have on thinking about fairness questions and the broad life cycle of building algorithmic tools. So for a bit of background, which would be useful for the discussion, there are broadly two large frameworks that are most common for thinking about algorithmic fairness questions. By far the most popular one are what I'm dubbing observational fairness. So these are tools that look at fairness from the lens of similar statistical properties of your predictive model across different groups. You could think, for instance, about accuracy differences or error differences in your model across different groups. You could think about maybe more nuanced notions of differences across groups that look at false positive or false negative rates and the like. And so this is by far the most popular way of thinking about fairness questions, and it's focused on overall population differences across the different groups. Along similar lines, there's also an individual fairness notion. So here, the idea is to go from thinking about overall groups to thinking about individuals within the groups. And so the notion of similarity that one is pursuing is thinking about building methods that make similar predictions for similar individuals. And we'll spend some time on this later, but as you might imagine or already know, one of the difficulties in this framework is thinking about what similarity means and how that similarity then affects the tools that you're building. The other large set of approaches for thinking about algorithmic fairness are around causal definitions of fairness. So a large class of these methods think about interventions, which are a common tool in causal modeling broadly. And the idea here is if I intervene, say, on a sensitive attribute, so to be specific, for instance, if I intervene on the sex or the race of an individual, how does the prediction change? And so this gives you some sense of what the model is sensitive to in a causal interventional sense. And it's closely related to the group fairness view of things. And then there's also more individual fairness notion. One example of this is what is known as counterfactual fairness, which has a bit more technical definition in terms of intervening on a particular individual as opposed to generally on a group or a particular sensitive attribute. There are extensions of this idea to things like path-specific fairness, which you won't spend any time on, but I'll mention for completeness for anyone interested. So within individual fairness, the main question, as I alluded to earlier, that people will often be asked is, in defining a metric, which individual should be treated similarly? So what is your notion of similarity? There are lots of frameworks for this. One that I find somewhat intuitive and sort of useful for explaining things is to think about taking your data and partitioning it into a set of cells, so sort of small partitions of your data. And within those partitions, you want the same predictions for all the individuals. And you can use standards of limit arguments to make the partitions as small as you like in order to get down to an individual. So for our working definition, for simplicity, we think of individual fairness as sort of very small groups. If you extend this idea a little bit and you allow for larger groups, and in particular, typically you allow for groups defined by sensitive attributes, which we'll spend a bit more time on in a bit. Then you come up with an approach or definition known as group fairness. So here the question is typically posed that as what property of my model should be equalized across my different groups. So there are lots of examples of group fairness measures that are in common use. By far, probably the most common is to evaluate some kind of accuracy or error for each group and then ask for the differences across different groups in terms of accuracy or error. But you can also look at specific rates, and they're good questions related to harms for why you might want to look at, for instance, true positive rates or false positive rates and see how they differ across the different groups. And I'll refer you to the papers for a bit more detail. And then a very common notion, which is roughly thinking about just how often I make positive predictions, where positive is thought of as the outcome that is favorable to an individual. You could look at how often you make positive predictions across groups, and this is known as demographic parity. So this is looking at notions of group fairness from the point of view of model statistics and how they differ across groups. Another way that's also roughly equivalent is think about things in terms of conditional independence. So I want different either my inputs, my sensitive attribute, or the target label in the supervised setting to be conditional and independent of each other in various ways. And again, citing the same textbook that Olga cited earlier, the Fairness in Machine Learning textbook, I'll refer you there for both a large variety of measures, so examples of metrics that people have come up with, how they're related to different notions of independence that might be interesting, and also some early references for many of these works in terms of some early definitions. And also, typically these definitions include some motivation for why these might be interesting ways of thinking about fairness. In addition to individual and group fairness, there are also, I mentioned briefly, causal approaches to fairness. I'll just cover this at a somewhat high level, but roughly the idea is that you posit a causal graph, which is a model for the data generating process for how your data arises. And then your goal is to understand how interventions on the sensitive attributes or interventions, counterfactuals on individuals, affect differences in the predictions from your model. And this then tells you something about a notion of fairness related to either interventions or counterfactuals. Now, in all of these approaches, maybe barring to some extent the causal fairness approaches, one of the hardest questions to try to answer is how to pick the metric that you're going to use. So in the individual fairness setting, as I mentioned, this metric is determining similarity between individuals. In the group fairness setting, this is most commonly used to define what statistic you want to make similar across different groups. And this is further made challenging because you can show quite easily, and I'll give some examples in a minute, that fairness metrics are not exchangeable and in fact can contradict each other. I'd argue that this is not special to fairness metrics. So while I'm going to focus mostly on fairness metrics here, it is indeed true that most metrics we use for most learning problems also have the similar property of not being necessarily exchangeable, where improving one metric can actually make another one worse. And so this makes the question of defining a good measure for fairness often quite challenging. So one case where this has come to a head, and I'm mentioning this not so much because of the application, but because it's one of the cases that actually got into common consciousness as an important setting, was recidivism prediction. So this is predicting risk of reoffense related to sentencing. And so in this setting, there's a company that built an algorithm, and many of you might have seen this before. If you've been to any fairness tutorial in the past few years, you've probably seen this slide at some point. But here I'm going to focus on the differences in views of measures of fairness and then use that to motivate thinking about ways of picking metrics. So in this setting, the company developed a recidivism prediction method, and they focused on calibration as their notion of fairness, and ended up releasing the algorithm, ended up being in use. And ProPublica analyzed the results afterwards, and they found very stark differences in error statistics, in particular false negative rates and false positive rates between different groups. And so they wrote, I'm quoting here, that Black defendants were twice as likely to be incorrectly labeled as higher risk than white defendants. And conversely, white defendants labeled low risk were far more likely to end up being charged with new offenses than Blacks with comparably low COMPAS risk scores. And so, of course, this is somewhat complicated application of algorithmic tools, but one issue I want to highlight here is here's a setting where two different teams had different ways that they were thinking about what fairness might mean, developed methods that satisfied those notions of fairness, and ended up with very different kinds of methods, very different kinds of analyses of the resulting algorithm. And this idea ended up being developed a bit more. And so you might have heard of the term of impossibility results, which has mostly been analyzed in the context of group fairness classification. And the underlying idea here is that while you'd like to be able to define sort of a unique best metric or be able to satisfy many, many notions of good prediction simultaneously, it turns out that you generally require a trade-off, and often you can't satisfy many notions at the same time. And so I'll refer to a paper by Kleinberg that talks about inherent trade-offs in fair determination of risk scores. So in binary classification, you can show that you can match at most two independent statistics. You can increase the number of independent statistics you can match for more complex, say, classification tasks like multitask classification. Roughly in classification problems, this flexibility grows with the number of classes, roughly quadratically. So you can define more and more measures that you want to agree across different groups and actually satisfy it. And so again, this shows that there's a fundamental bottleneck here in thinking about the kinds of fairness guarantees that you can give. You can't satisfy all measures that you think are reasonable at the same time. Maybe thinking a little bit more about metrics, I think there's maybe more thinking about the good and bad of metrics within the field broadly. So you might hear of arguments, and maybe I'll argue here for what is good and what's great about metrics. So it's definitely appealing to think about optimizing, say, a single true metric. And metrics, I think all of us will agree, are great for rapid advancement. So many of the areas of the field that have grown most quickly, I think have grown because there was a data set, there was a measure, and it was clear what advancement actually meant. And so you could just hack at the problem very quickly and make a lot of progress. I think there's also some arguments that you might hear about what I'm calling measurement fundamentalism. So the idea is if you can't measure it, you can't manage it or you can't improve it. Sometimes this is attributed to Peter Drucker. But also I think applies to machine learning views of building models. So this idea is, again, anything that's not measurable doesn't matter. Now I'll give some arguments for why this might not be enough in a couple of minutes. On the other hand, thinking about where we think metrics might fail, you might argue that metrics reduce complicated problems into sort of single numbers. And once you've made this reduction, you've lost a lot of detail about what's complex about the model or the data or the application setting, because all you have is this number. And so this reduction may actually lose too many important parts about a problem. Another maybe concern about fairness is while, again, it encourages chasing a state of the art in this rapid advancement way, sometimes it's unclear that actually advancing the state of the art in this way actually solves the problem we care about in a meaningful way. And so one could argue, and many have, that state of the art chasing actually is misleading the field in many settings. Another, I think, useful view of maybe some downfalls of metric chasing is what is sometimes known as Goodhart's law. And the idea here is that once you've defined a measure as the target, it ceases to be a good measure, because once you define it in this way, there are often ways that you can game the system in order to sort of get around what is meaningful or what's interesting about a problem, to think about it purely in terms of metric chasing. And so one interesting view that has emerged over the past few years to try to advance how we think about measuring both performance, but also more recently fairness in different kinds of models we're building, is an approach called metric elicitation, which I'll overview in a few minutes. And the broad idea is that it provides tools to adapt the way we measure models, measure fairness to the context and the stakeholders. And the way it does this is that it reverses metric selection into a sort of human interaction problem. So one framing of this from Hirandani et al., this is work I was involved in, is the metric elicitation framework, which tries to determine both the fairness metric and, say, the performance measure by interacting with individual stakeholders. The idea is that I take some model, I convert it into the set of statistics that I'm interested in, and then I try to come up with queries that are cognitively easy for stakeholders to answer, that might get at their underlying preferences that best measure, say, what notion of fairness might make sense for a certain problem. And so you construct these queries, and in these lines of work, there's a lot of effort spent on both cognitively easy queries and also on query complexity. So what you want is that this is fast, because as you might know, any of you that have done work with humans, people get tired quickly and it can take a long time. And so you want to make this as query efficient as possible. So how can I solve this problem using as few queries as possible? There've been extensions of this work to think about beyond single individuals to having groups of stakeholders and ways to elicit preferences from these groups. And in this line of work, I'll mention a pilot study where we looked at specifically thinking of binary classification and underlying confusion statistics, and how different HCI approaches can be used to make it easy for stakeholders to understand what confusions mean and then compare between them, you know, to tell us preferences between different kinds of models. Beyond this line of work that I just explained, there are a few other approaches that have come out in the literature thinking about ways to elicit primarily group fairness. So one approach I like, makes sense in many settings, is in Aquitas, I hope I said that correctly, which essentially just sets up a simple decision tree, ask simple questions about whether, for instance, it's an assistive or punitive application, whether you can intervene with most people or only a small fraction. And based on these, gives you a simple tree that you can follow to come up with one of a small set of metrics that might make sense as a useful metric of fairness in this setting. Another line of work from Zhang et al. Looked at simple sliders. So this is a bit more direct, maybe a bit more cognitively heavy, but it requires you to know, to be able to say, for instance, what is more important, increasing profit per applicant by 100 or reducing differences between young and aged people by 10%. And so the idea here is to try to get a sense of how important the performance measure is versus, say, the fairness criterion as a way to set a trade-off between those two ways of measuring what the models are doing. Beyond the group fairness context is also work in individual fairness, thinking about ways of eliciting metrics. So here often there'll be questions about differences in predictions between two models, or differences. So you would say fix two classifiers and see how they predict different sets of examples, and try to use this information as a way to pinpoint good individual fairness measures. Remember here, for individual fairness, the measure or the metric is how similar two individuals are. So which two sets of individuals, or which sets of individuals to be treated similarly. And so there's I think a growing line of work trying to, if you like, bridge this gap between better measures that better capture good notions of fairness and the algorithmic tools that we're building in order to actually target those measures. However, though, or maybe taking a step back, I think it's worth again repeating that I mentioned this briefly, but in many steps in the pipeline of constructing algorithmic tools, we have to make, I think, very strong reductions, and these reductions matter. So in particular, I think two that are important to mention. One is when we select variables. In particular, most importantly, when we're dealing with people-dependent type prediction problems. So generally, you can't measure people completely, so you look for a set of variables that you think are important. Say in a loan setting, you might look at, say, their history, credit score, history related to repayments, things like that. So these are features that you think are relevant to the prediction problem at hand. But by definition, these are reductive because these are only looking at a small set of characteristics related to an individual. Yet it's important that you make those reductions. One, because we have finite compute, in order to solve these problems. And also we know that high dimensionality can cause sometimes issues with noise, or might require more sample sizes to solve problems accurately. And so this reduces or results in, I think, sometimes hard questions about which variables we should be using. There are often also confounds, which I'll talk about in the future, so I'll just mention here, which are common in real data, but can also lead to confusion and sort of the usefulness of variables for a certain prediction problem. I also mentioned this, but I'll mention again. So metrics, by definition, have to reduce complex problems to single numbers. I mentioned this because you'll sometimes hear the arguments for a particular metric being sort of better than another one because it completely solves a certain set of questions. I think this may be too narrow, because all measures, by nature of this reduction, have to make choices about what's important or not important. And so we'll, by definition, have blind spots. We'll talk about this a little bit more later. One example, one story that I really like in terms of bringing this home, this idea of reduction and incompleteness and specification of problems, is an example that I heard from a talk by Sarah Wacha on AI training related to law. So it's actually not a completely different topic, but I found this compelling, so I'll mention it here. So many of you, or some of you might be familiar with an idea in mechanism design. This is sort of classic CS theory known as fair division. So the idea is that I have some good, and I want to divide this between a set of individuals in a way that I consider fair. So this, I think, is a problem that shows up a ton. And I think the classic definition of this problem and the classic solution is extremely appealing. In particular, you can show, for instance, that if I have the simplest setting of this, the picture I have here is a slightly more complex setting. But in the simplest setting, you can imagine that I have a simple good. Say I have a nice cake, and I want to divide this between the two people. The solution, if I'm thinking of fairness in the way that it's classically defined, is that one person cuts the cake and then the other person selects the slice. And they know the rules ahead of time. And if you do this, then you're reasonably certain that whoever cuts the cake will do it in such a way that they don't actually disadvantage the other person, because then the other person gets to select the slice. So this ties to incentives of people and makes a lot of sense. However, one thing that was mentioned in this talk was, well, suppose you knew that one of the individuals, so to give names is Damien and Cleo, suppose you knew that Cleo hadn't eaten in a solid food in 2 days. Would the answer to this problem still be the classic fair division problem with the simple solution as just described? And so I think what this example highlights is, again, there's a ton of context that ends up being missing when sometimes we simplify problems in ways that are easily solvable. And this missing context is important because, or could change how you approach or solve different kinds of algorithmic questions. I also wanted to mention what I found an interesting article. This is mostly a pointer for people to take a look later, so I won't do a deep dive in it. But it's an article from Dork et al. On abstracting fairness, oracles, metrics, and interpretability. And they take an abstract view. So they think of metrics mostly as differences between machine learning models. And their notion of metrics, specified metrics, is sort of tied to elicitations. It's the idea of using human judgments to define and analyze metrics. And so it's broad enough that it applies to both the observational and causal framings that I highlighted earlier. And they make a strongish claim in the paper, so I encourage you to read it. It says that essentially a metric is always at the heart of fairness. And their definition of this is that, again, in order to use algorithmic tools in these settings, and in order to, and if we think that humans are good arbiters of what fairness should mean, then there must be some weak notion of metric under the hood that says which classifiers are better or worse, or which models are better or worse. And so you could argue from that point of view that there's an underlying notion of metric sort of anywhere in a fairness problem. I thought that was an interesting aside related to interpretability. Again, I'll have you read this on your own if you're interested. But I think there's some interesting connections between ways of thinking about fairness and particular elicitation, and what's important or interesting about various kinds of models, and interpretability. So to what extent can interpretability tools give us insights that help us to decide useful or fair properties of different kinds of models? Okay, so to summarize the second narrative, so we've argued, or one could argue, that metrics are the key, maybe the most important step in algorithmic fairness. On the plus side, I think the argument is that maybe a purely applied argument, we know how to do this well. So there are lots of tools once we've defined, or we've chosen our metric and framework. We also know that once you define the metric and framework, it's somewhat easier to sort of work on those tools. I argued or mentioned briefly metric elicitation, which I think is a promising approach to help select metrics, but I think it also has potential issues that need to be thought through. So it requires that you trust the stakeholder judgments in a way that's hopefully unbiased. And we know that humans have biases, so everyone comes with their own biases, which is separate from any notions of fairness, coupled but separate, if you like, because I can't think of a better phrase right now. And so this ends up potentially confounding the extent to which we can use responses as good ways to specify fairness metrics. As mentioned briefly, I think metrics are not universal. I've argued that they're context and stakeholder specific. And in particular, often will have specific blind spots and failure cases. And so I think it's useful to state that you should not only evaluate metrics on, say, just training and validation data, but as many of you would know, you should be thinking about the fairness measures of your model post-deployment. So what happens if I've actually deployed these models into the world, and how are these models actually performing? In particular, because of all the interesting ways that distribution shift can interact with models. And we'll talk about this a bit more in narrative 6. Finally, I think it's useful to argue that metric selection should not be done once. So by construction, you have to pick what properties you care about when you're selecting a metric. However, you might find new things that you want to improve once you've developed your model and, say, deployed it. And so it's useful to continuously audit after deployment and try to improve the metrics to address unexpected failures or new things that come up after you've constructed or deployed your model. So that's it for narrative 2. Maybe we'll pause for a couple of questions before moving on to the next one.
If you have questions, so I think that microphone should be connected, but I think Sammy should be able to hear you.
Yes. So I was thinking about, you mentioned Goodhart's law, and I wonder if we focus on fairness as sort of as a continuous metric might be a bit of a problem, because, for example, when it comes to accuracy, a model that is 51% accurate is objectively better than a model that is 50% accurate when it comes to your accuracy. But with fairness, we're typically concerned about it because of underlying biases in the data, right? So the reason why a lot of models that classify people of color as having one emotion versus white people is because our data is biased. But once you sort of rectify that, some measure of fairness, there might just be like a little wiggle, right? Do you think that maybe if we start thinking about fairness as continuous, we want to continually improve it, just like classification, we might start actually missing the underlying problem, which is the way that the data
Yeah, so I'll repeat parts of that because I think I got most of it, though it only partially, the mic only partially worked. What I think I got from the question was, it might be useful to think on binary notions of fair and not fair, and think about continuous notions that capture degree as opposed to binary notions. Fully agree. I think in particular, binary notions are extremely hard to achieve, and I think as you've mentioned, are not always that meaningful. I think some of what has been argued as well is that if you focus only on binary notions, sometimes this leads you in a weird hole where sort of the only solution is a constant predictor, for instance, that has no signal. And so you actually do need to allow for some of the gap, I think what you called wiggle room or a term like that, as a way to better allow for thinking about different trade-offs between different notions that or different properties that you want your model to achieve. I think that's a useful view. I think maybe extending on that view a little bit, a lot of the field has gone towards continuous measures for, say, differences between groups. And on top of that, also thinking about trade-offs between those different measures and also trade-offs between the fairness properties and, say, the performance properties of your model. And so thinking about everything as this big continuous mix of trade-offs between a whole bunch of different properties, I think can be a useful view from a point of view of or just actually solving or actually getting a sort of some solution that can be helpful. I think it's useful from a point of view of usefulness in the real world and the fact that the real world often also has these nuances. And so it's hard to make these sort of binary outcome decisions for something as complex as fairness. I would agree. I think we might, as we cover some of the other narratives, some of that might come back and it might be fun to discuss a bit more. Thank you.
All right, I think if there's no other questions, so we're going to do, well, 2 more narratives before the break, but actually it's 1 narrative and then 1 slide on the 4th narrative. So we're basically 2/3 of the way to a break here. We can do like a, 1 minute, just like stretch break. I know it's sort of sitting for an hour and a half. It's hard. So you're welcome to do that. Let me make sure I'm. I think if I'm talking, it'll spotlight me rather than Sammy.
I think it does.
Okay, if I just like keep talking, it will pop up again. Okay. Brief stretch break. All right. Okay. So now that we have sort of some sense of metrics, or at least some attempt to try to quantify, right, what it is that we're, oh, sorry, one more thing. Okay, some attempt to quantify sort of what it is we want to do. So let's come back to questions specific to computer vision. Let's come back to, I guess, so the question of bias in data sets is actually not specific to computer vision, but the data sets that we're going to be talking about are computer vision data sets. So to what extent is bias present in data sets, and sort of to what extent can we try to mitigate bias in data sets such that, whatever downstream metrics we define are actually kind of satisfied perhaps at the data set level, right? If we don't collect biased data, then maybe, the downstream problem becomes easier. So, sorry, it's still not showing me. I wanted to show. Maybe that. Okay, there we go. So as we talk about data set bias, right? So data sets and their role in machine learning. So we have to go back to the Traubman-Efros, the Antonio Traubman-Efros paper from CVPR 2011. If some of you hopefully remember this paper, I thought this was an awesome, extremely influential paper that talks about how every data set is a biased slice of the visual world. And so the example that they gave back then is they had this great figure 1, which is 3 images from 12 common computer vision data sets. And if you were working on visual recognition back in the day, you could 100% match the 3 images to the particular data set. So I remember I was a grad student at the time, and this was quite easy because all of these data sets we worked on, and they're just so different. So, and they pointed out that, right, every data set, even though we like to think that something that's built on this data set is representative of the whole world, in practice, right, because we can uniquely identify from just 3 photos of the data set which data set it belongs to, it means that the data set has a particular distribution. It sort of models the world in a particular biased way. And this has persisted to today, even as the data sets have gotten larger. There was a paper that came out of the NeurIPS data set and benchmark tracks last year that pointed out, sort of talked about AI and everything in the whole wide world benchmarks, and kind of cautioned us again against thinking of every benchmark as sort of representing the whole world and capturing everything in the world, and sort of said, no, look, every benchmark, I mean, we need benchmarks to make progress, perhaps. So we need this common task framework, right, to rally around particular metrics, although we should be really, really, really careful about what exactly these benchmarks are, what exactly these metrics are, and not to overclaim, essentially, to sort of view the benchmarks for what they really are. And one question with benchmark collection, and particularly with sort of in the context of fairness and in the context of bias, is do we want our benchmarks to represent the world as it is? Do we want to mirror patterns in the world, or do we want to adjust that? Do we want to sort of collect data that's different from the way the world is right now? And one example of this that I'd like to give, just because it's a very compelling example, is that if you're collecting an autonomous, so forgetting about fairness first, you're collecting an autonomous driving data set. You can drive around and collect, sort of all of the data that's coming in, and that's great. But in practice, what you want to do is you want to focus a lot more on dangerous driving situations, right? The boring, simple, nothing is really happening. Those situations, they're the most common, but are not the most interesting, or arguably not the most important to get right from building a computer vision model for autonomous driving perspective, right? So you might want to focus, and people do in building the system, specifically on some scenarios that maybe are less common but more important. And so all of this sort of comes up as we start talking about fairness and like what's represented in data sets. So when we think about the going from kind of real world to selection for inclusion in a data set, so I want to kind of highlight 3 different things. So one is over or under sampling of different demographics, as well as stereotype portrayal, which is sort of a slightly more complex version of this, of sort of who and how is represented in the data, and then conclude very briefly again with consent and privacy. So if we think about over and under sampling of demographics, this is kind of maybe the most canonical thing you would be thinking about if you're thinking about fairness in computer vision data sets. So a lot of the time, actually, when we talk about overrepresentation or underrepresentation, we don't always actually have a very clear notion of ground truth, of sort of like what is the right representation or the target representation, or sort of the target distribution within the data set. But one paper in particular, so this is a paper from Kai 2015, that studied, so this is not a computer vision data set, this is web search results, but of course we pull from the web all the time for constructing our data sets, so this is closely related. So they looked for, they analyzed web search results for when querying for photos of people of different occupations. And they plotted on the x-axis the percent of women in these occupations, right? So they actually have they define a notion of kind of ground truth, or sort of target distribution, right? There's a particular percent of women that are in these occupations, and then on the y-axis they can plot the percent of women in image search results when querying for this occupation. So the diagonal line, right, is where you sort of want to be. And one of the things that they've observed, right, is that when you have more than half, when it's an occupation that has more than half women, more than 50%, the percent of women in image search results actually kind of follows that line, loosely speaking, right? So that there it's Essentially kind of follows that trend. But as soon as you drop to % of women to occupations which have fewer women, it actually appears to be that the percentage of women in the image search results is actually even is lower, is below 50%. So that means that, right, if you were to flip this graph, so men are represented in these search results even for occupation, sort of consistent with their frequency in the applications when they are the minority, and when they're the majority, they are then they become sort of overrepresented in the search results. And the other thing that this paper pointed out is, they're referring to as a sexy construction worker example, that for the occupations where there's very few women, when the women are represented in the search results, they tend to be a very stereotyped view. So for example, if it's a woman construction worker, she's going to be depicted as a sexy woman construction worker. So this, we'll come back to this in the question of stereotype representation. So how do we study demographic distribution in computer vision data sets? So one of the earlier studies of this was the face data set. So this is the gender shades work that we've already referred to. This is the one that studied the discrepancy in error rates on faces of lighter versus darker skin. This work by Joy Belomini and Tina Gebru in 2018. So they went ahead and annotated 2 common computer vision data sets with perceived gender of the people in the images and perceived skin tone, so lighter versus darker skin tone. And they found that common computer vision data sets are about 80 to 90% people with lighter skin. And so this is this is not necessarily the cause for why face recognition systems at the time performed so poorly on people with darker skin, but this certainly didn't help the situation. So this certainly was a problem. It was, I think, in some ways a surprise to the community. This was an important result that I think many people in the community were not aware of. The data set at the bottom is the Parliament benchmark data set that they collected, which was more balanced. So some other examples, right, of demographic distribution. So this is our work at FACT in 2020, where we annotated the distribution of people within ImageNet, so specifically within the person subtree of ImageNet. And so here on the x-axis, you see synsets or categories in the data set, and the y-axis, you see the percentage. And so this is trying to annotate gender, trying to annotate skin color, trying to annotate age. And again, you can kind of see, here there's no particular kind of target distribution, but you're trying to get a sense of generally what is happening in the data set, sort of who is appearing in the data set. And similarly, again, this is also our work from ICCD last year. So annotating race and gender, or I should say, I'm going to caveat all of these annotations in a second, but essentially annotating gender expression and lighter or darker skin tone on Coco. And again, you see sort of similar things, arguably overrepresentation of people of lighter skin. So basically, again, we can talk about what the target demographic distribution should be, but for now, you can see that it's about 63% people with lighter skin, and it's only 20% female versus 50% male. Data. So how are all of these done? So I'm sort of, I kind of jumped into this and said, okay, we can annotate demographics from these data sets to try to understand biases in the data set. Okay, so how is this actually done? Because these are large scale data sets. How do we actually annotate demographics and get any kind of sense of what's happening in the data? So some of the early efforts, this kind of annotation was done using automatic systems, right? So the early effort to study, for example, the demographic distribution within ImageNet was done using models for gender and age and skin color. So of course you can get some statistics, but this raises concerns about bias in the models, right? How can you trust these statistics if you're not quite sure what is, whether the model itself has bias, right? It kind of creates a chicken and egg problem. So the next kind of set of efforts, which is actually still, these annotations are still being very actively used right now. It's indirect annotations through image captions. So on Coco, for example, we've collected image captions. And so now if we're trying to study the distribution of gender in particular here in the images. So the way that they did this, so this is best paper award from EMNLP of 2017. So they took the 5 associated image captions on the COCO images. If any caption mentions the word man or woman, then they mark that image. If any image has captions that mention both, they will remove that image, and otherwise that's your binary gender labels. And of course, again, there's concerns about accuracy and bias of these labels. For example, there's works that have shown that these labels are biased towards male, biased in a particular way where sort of when in doubt, the annotator is more likely to say male and sort of use the word male or the word man as a proxy for person. And so when you derive then gender labels from these captions, you get this kind of shift towards so man kind of means I am not sure, or this is somebody who perhaps looked like a man. And so we've estimated about 80% agreement of these labels with human annotators. Now, the kind of most common way of studying this is, of course, through annotating using mechanical turn orders. So this is, of course, there's the cost question of, actually being able to obtain these annotations. And this is why frequently we still have to revert to these sort of imperfect automatic methods. But the common way, right, is you are going to annotate using mechanical turn orders. So first of all, there's increased push in the community to actually try to collect and analyze worker demographics. So, and lots of papers have sort of point out that as we try to do this fairness work, right, and as we try to understand the fairness, sort of the demographic distributions in our data sets, so who is actually doing the annotation of these demographics? And we know that there's definitely bias in the human annotators. So depending on which demographic groups the annotators themselves come from, they may be inferring demographics for the depicted people differently. So that's the first thing I sort of want to flag. The second thing is whenever we talk about studying gender, right? So what we're really talking about, particularly in computer vision context, so we're talking about binarized, inferred, perceived gender expression. So this is not gender identity, right? Gender identity is much more complex. Gender identity may not align with gender expression. Gender identity is not binary. And so we make already all of these simplifications, even just in the annotation process. And frequently when we are talking about fair, so Asima was talking about the metrics, right? A lot of the time for the metrics, we're talking about, let's say, 2 protected groups. And if we're talking about this in the context of gender, like just keep in mind what this actually means in terms of the sort of in the real world in terms of gender. So similarly, whenever we talk about fairness in race, we're talking about race approximated by skin color. And so this is typically annotated on a Fitzpatrick scale from 1 to 6, and or just classified as light versus dark skin, right? So this is not the same as race. Particularly, there's this great quote from people, right? Alex Hanna and her collaborators called Towards a Critical Race Methodology. It says current methodologies fail to adequately account for the socially constructed nature of race, instead adopting a conceptualization of race as a fixed attribute. And not only that, it's a fixed attribute that essentially boils down to skin tone. So all of this is essentially trying to give you some context of how we are currently thinking about bias and fairness in computer vision data sets, and sort of what are some of the issues or nuances there. One question we might ask at all is like, is demographic annotation acceptable? And so there's a couple of ways of thinking about it. So you could say, well, we need to study aggregate distribution on data sets. Like if we don't do any demographic annotation, then we can't study fairness. So we kind of have to. And we can argue, okay, it might be acceptable for studying aggregate distributions on data sets. So you could say, yes, it's acceptable. There may be individual errors, but they won't matter at large scale. The counter to this is you could say, well, no, like it is not acceptable because there's going to be errors in these labels. And these errors are going to be harmful. So there's going to be people whose gender identity, whose racial identity, whose age are going to be inferred incorrectly. You could also make the sort of technical argument that this is unacceptable because aggregate distributions will have accumulated stereotype errors. So again, depending on the demographics of the annotators and also just generally depending on our own biases, right, we may be kind of consistently making annotation errors on people of certain groups. So one of the most compelling arguments that I know actually in favor of demographic annotation is the argument for accessibility. So the argument is, yes, it may be accessible to do, and it may even be okay to automatically infer demographics because we need to build one of the applications of computer vision systems is assistance for people who are blind or people with vision impairments, right? And so there's some great papers connecting with various communities, particularly sort of blind or low vision individuals, and asking them, what kind of descriptions would you want to appear in automatic captions? And also connecting with people who are members of particular minority groups who are blind or low vision, asking them, how would you like to be described in these captions? And so in this case, right, this demographic annotation, yes, it is problematic. It can be problematic, but also it has this potential very important downstream benefit. So the last thing that I'll say here, so I get excited talking about this. So the last thing I will say here is the question of like which axes of identity this has come up earlier to actually include when studying these demographic distributions. So excellent question. So there's no easy answer. So frequently we will look at basically gender or skin color, lighter or darker right now for studying this. Of course, we are trying to go beyond single labels. This is sort of where the community is heading right now. Point out the term intersectionality, which is coined by Kimberly Crenshaw in 1989. I will actually read this quote from her. This is from an interview that she gave in 2017 about the importance of intersectionality. It says, intersectionality is the lens through which you can see where power comes and collides, where it interlocks and intersects. It's not simply that there's a race problem here, a gender problem here, and a class or LGBTQ problem there. Many times that framework erases what happens to people who are subject to all of these things. And so as we think more and more about algorithmic fairness, right, there's a push of thinking about intersectionality in machine learning, and I will do kind of a shameless plug here for a paper at FACT being presented this week that kind of tries to grapple with what happens as you scale up to these more complex demographic groups and sort of intersectional identities when doing machine learning fairness. And the summary of the paper is basically you are trying to consider the social context, but also do empirical analysis to figure out what's sort of right from a machine learning perspective. Okay, so we've talked a little bit. I know I'm not giving any kind of conclusive answers, but we've talked a little bit about at least how do you study demographics and how do you perhaps think about sort of over or under sampling or ground truth of demographics and data sets. So let's talk just very briefly about stereotype portrayal, right? So this is kind of thinking back to the sexy construction worker example. So what happens when the statistics in the data set suggest that you have an equal balance, say up to genders or an equal balance or sort of a good target balance, but then how are these people actually represented? So I'll talk very briefly, I'll give you, so again, this is, the tool that I already mentioned, so Revise, which is trying to measure and mitigate bias in visual data sets. So here we're, this tool takes as an input a visual data set and some kind of annotations, basically whatever annotations it can get its hands on, plus some automatic methods. So some automatic pre-trained models is needed. So here I'm showing on the x-axis is the, so let me do the y-axis. So the y-axis is the scene categories. So these are automatically predicted by a network pre-trained on the places data set. On the x-axis, I'm showing the fraction of images with this particular scene with people who appear to be male or female. So these are annotations actually obtained, again, imperfectly derived from the image captions, but trying to analyze sort of overall distributions of the data. And in the second graph, so this is the particular objects that appear in Cocoa that were annotated. Again, on the x-axis, you see the fraction of images that contain this category with people who appear to be male versus female. And so you can start to see these like discrepancies in distribution where even if you balance the data set such that there was an equal number of male and female, they may be present in different scenes, which means that as you start training models on this kind of difference in portrayal may propagate to downstream models. Do another very quick example. So this is an analysis on the open images data set. So here we're learning visual classifiers for the object when it's present in photos with people labeled as male versus female. And we're trying to identify object classes with the most stark differences between genders, right? So even if this object class appears equally with people of both genders, does this object class look the same? And so one object class that popped out was sports uniforms. So it appears that people who appear to be female, the kind of sports uniforms that they wear are quite different than for the people who appear to be male. And this is in line with some of the social conversations that are happening in the real world around sports uniforms. And similarly for the objects like flower, right, might have similar co-occurrence statistics, but look quite different. And finally, so this is kind of a stretch, but I thought a sort of an interesting analysis that we have, which is you can try to ask who is taking the picture, back to the kind of geography questions of fairness. You can try to ask the question of sort of who is taking the pictures and of what. So here we're running analysis on the Flickr 100 million data set. The data set is, comes from photos all over the world, can do that analysis, but actually we're looking here at the percentage of tags for the photos. So given that an image comes from a particular country, what is the percentage of tags in non-local language? Now, this is a very imperfect measure, but part of what we're trying to say is, or at least kind of raise the question is, I wonder if in some of these countries, the photos are actually being taken by tourists, right? So they may not be taken by locals because they're tagged in a non-local language. And so they're being uploaded to these data sets. So even if we just look at the kind of distribution of photos, we can say, okay, this country, there's a lot of photos that come from this country, so maybe this is fine, it's well represented. There may be kind of additional complexities around sort of where these photos are actually coming from. So when we think about data collection practices, right? So the key limitation here is available time and money. So image search engines are going to be the most common source of data. And as we collect photos from the web, we're going to be grappling with some of these issues of how are different people represented in these photos, not just in terms of frequency, but also in terms of sort of what they look like, what the context looks like. And there's been efforts in the community more and more to give more credit, attention, and focus on data collection. So for example, this work called Lessons from the Archives that argues that computer vision dataset curators should really be thinking of themselves more as kind of archivists, as this really should become a almost a discipline that's focused on data collection rather than being kind of a part of machine learning that's somewhat sidelined. And so the NeurIPS datasets and benchmarks track that was started last year is part of that effort to really give some an intellectual home, if you will, to data collection. Start engaged with some of these issues. Bias in search engines, right, leads to bias in collected images potentially, which also leads to bias in included images. So I'm not going to dive into that whole pipeline. We have some analysis of that. Again, sort of pointing to some literature if you're interested in learning more. But I think based on everything we've been talking about so far, this should come as no surprise, right? So if we're relying on image search engines to do the data collection, there's bias there, which is going to make its way into the collected images, but also as data set collectors, we're making some decisions about which should get included in the data set. And finally, it's actually not clear if we even understand the target distribution of kind of what we are aiming to collect when we collect a new data set. And there's efforts like data sheets for data sets from Jimmy Gebru that argue for, at minimum, being very explicit about the intended distribution and use case of a data set. So rather than saying this data set, represents objects in the world, right? Okay, so what objects? How was this collected? What were the decisions that were made along during the data collection process? The last thing I want to sort of point out, right, with data collections, particularly with sort of bias and fairness, there is the questions of, again, of consent, privacy, and ethics. So legal guidance is evolving on this around what is acceptable or not acceptable to include in data set. And this is actually particularly interesting in the context of an international research community, because this is very tightly connected to the laws in different locations, right? And the laws are different around the world in different countries. Yet we are an interdisciplinary community here, an international community here at CVPR, right? So how will our data sets sort of evolve to encompass all of these different legal guidance around the world? And finally, I do want to put up all of these citations. I know it's a lot of citations, but there's a very, very large literature focused on computer vision data collection and focus on these issues of consent and privacy and ethics and what is happening with these data sets right now. You might notice, so all of these papers actually came out 2021, 2022. This is like a very, very active area. I'm not going to do it justice here, but I will absolutely encourage you to go and read at least some subset of them to try to understand what are some of the kind of evolving conversations about how to do data collection responsibly. All right, so discussion of narrative 3. So kind of said, okay, so there's an argument to be made that bias in data sets is inevitable, and what we need to do is learn to live with it. Learn to live with it and learn to sort of work around it in trying to build better computer vision. So what's the pro? So the argument in favor of this is that data sets will always be targeting a particular bias distribution. And these data sets will always be limited by the money, time, and energy of the data collectors. And so efforts like data sheets for data sets, right, so to me and collaborators' work are aimed at explicitly articulating the fact, sort of being very proactive about this, just sort of stating this and saying this is how it is. And then efforts like Revise and many other tools are aimed at evaluating claims of data set distribution and identifying additional data set biases. So sort of accepting that, yes, it's targeting a particular distribution. It's not perfect. Let's understand and be explicit about that distribution. But the con is, of course, so it's too fatalistic kind of to stop at the claim of bias is inevitable. Right, so there could be efforts made to reduce bias in data sets, and particularly, if you remember the example I used earlier with the face data sets, right, that were 80 to 90% lighter skin, right? That's a kind of bias that is an oversight that can't be mitigated and should be mitigated, right? So while you can say, sure, so in general, the data set will always be biased, but there are some kinds of biases that are just failures of the imagination, right? You can mitigate them. There's stuff you could do about it. And we need to differentiate between different types of biases, right? So different levels of harm, and some of the biases arguably are more innocuous than others. And again, legal and policy guidelines are shaping what is acceptable to include in data sets. I'm actually going to finish. So let me do so. So discussion narrative 4, it's going to be very related to this one. It's just going to be one slide. So let me finish that, and then I'll take questions on both. So the related narrative 4, which is the problem of data set bias are getting better. And so I hear this quite a lot, that basically this problem will solve itself. So I wanted to give kind of some brief discussion of this claim. So the pro here, right, is First of all, larger resources in the community, more acknowledgement of the importance of the centrality of data collection. So like the data sets and benchmarks track. So, we are actively focusing on this issue and are actively centering the data collection process more and more. You can make the argument that larger scale of the data set will mitigate bias. And again, the problem will solve itself with scale. So Alyosha Efros and Antonio Torralba in 2011 in the original paper with the 12 computer vision data sets, these are in the claim zone. Some of their experiments actually showed that when you combine a bunch of these data sets, or when you take the larger scale data sets, they have less bias according to their definition of bias, because by virtue of being larger. So that is true, I think, for some types of bias, right? So certainly if you just collect 3 photographs, they're going to have more bias than if you collected 30 photographs, provided you're trying to be fairly, if you go on the web and you download 3 photographs from a search engine versus 30, right? The 3 are going to be more biased. There's also an argument, so I'm not going to engage with this because I think it either needs like an hour of discussion or not at all, but there's claims that self-supervised learning make things better. I think this claim is arguable. So I think self-supervised learning in some ways can allow you to move away right from the necessity of labeling, which can move away from annotator bias and can allow the model to sort of automatically learn patterns of the data set in a way that is somewhat less biased according to some definitions. My big concern with this is that I think it's obscuring bias rather than actually making things better. But let's talk about the con, right? So the scale can mitigate bias, but scale can also obfuscate issues, right? So it's increasingly difficult to analyze these data sets because of their large scale. It is certainly true that certain populations are consistently left behind or excluded. So if you look at these demographics that I showed at the beginning, right, all of them across different data sets, different tasks, different annotation schemes, all of this is saying the same thing over and over and over again about who is being excluded from the data sets. And as the data sets grow in scale, that does not appear to be changing. And finally, it's becoming harder to democratize data collection. So the demand on resources, the cost of collecting a new data set is increasing. And so more and more, we don't have this diversity of perspectives in data set collections. It's the same groups, the same groups with a lot of resources that are doing the data collection. And this is not going to help with the data set bias. And finally, bias is becoming more consequential as the downstream applications become more consequential, right? So data sets that are being applied to very important downstream applications, the bias in them can do a lot more harm. All right, so I will pause here for questions before going for a break. Nobody wants to ask a question before a break. That's cool. Let's take a break, and then there will be time at the end for discussion. We can revisit this.